Hello chemistry students, Dr. Tellis here. In this section we will describe the units used to measure the levels of radiation, the amount of energy absorbed by human tissue, and the damage to human tissue. Several units of measurement are used to describe levels and doses of radioactivity. In the U.S., the degree of radioactivity is often measured in curies. 1 curie is equal to 3.7 times 10 to the 10th disintegrations per second, or DPS. Less commonly used in the U.S. is the SI unit, becquerel. Now 1 BQ is equal to 1 disintegration per second. The curie and the becquerel are used to report the amount of radioactivity when multiple kinds of unstable nuclei are decaying, and to report amounts necessary for medical purposes. By itself, the amount of radioactivity does not provide a good measure of the amount of energy in the radiation or the amount of damage that the radiation can cause to living tissue. Two additional kinds of information are necessary. The first is the amount of energy absorbed. The second is the effectiveness of the particular kind of radiation in causing tissue damage. The amount of energy absorbed by living tissue is measured in rads. RAD is an acronym for radiation absorbed dose. 1 rad is equal to 0.01 joules of energy absorbed per kilogram of tissue. The SI equivalent of a rad is a gray, and 1 gray is equal to the absorption of 1 joule per kilogram of tissue. Now, different forms of radiation cause different amounts of biological damage. The amount of damage depends on how strongly a form of radiation interacts with matter. Alpha particles cannot penetrate the body any further than the outer layer of skin. If alpha particles are emitted within the body, however, they will cause between 10 and 20 times the amount of damage done by gamma rays, which can go entirely through a human body without being stopped. In determining the amount of biological damage to living tissue, differences in damaging power are accounted for using a quality factor. This quality factor has been set at 1 for beta and gamma radiation, 5 for low energy protons and neutrons, and 20 for alpha particles or high energy protons and neutrons. Biological damage is quantified in a unit called REM, Roentgen equivalent man, which is based on amount and the type of radiation. A dose of radiation in REM is determined by multiplying the energy absorbed in rads by the quality factor for that kind of radiation. The rad and the REM are very large in comparison to normal exposures to radiation. So it's more common to express exposures in millirems. The SI equivalent for the REM is the sievert. Here's a chart looking at radiation exposure of an individual for 1 year from natural and artificial sources in millirems per year. Now, exposure to a small amount of radiation is completely unavoidable. Earth is constantly being bombarded with radioactive particles from outer space. There's also some exposure to radioactive elements that occur naturally on Earth, like carbon-14, potassium-40, which is a radioactive isotope that occurs naturally, uranium-238, and thorium-232. For some people, medical procedures using radioisotopes are a significant contributor. The average dose of background radioactivity to which a person in the United States is exposed to is about 200 millirem per year, which we can see from this chart. Well over half of that amount comes from natural sources over which we have no control. Of the 60 to 70 millirem per year exposure that comes from artificial sources, nearly 90% is delivered in medical procedures like X-rays and radiation therapy. Considering the controversy surrounding nuclear power, it is interesting to note that less than 0.5% of the total annual background dose of radiation the average person receives can be attributed to the nuclear power industry. The effective radiation on a person depends on the dosage and the length of time of the exposure. A series of small doses have less overall effect than a large dose given at once. A single dose of 500 rems is fatal to most people. Detectable effects are seen at dosages as low as 30 rems. Background radiation averages about 0.1 rem per year, but varies dramatically by location. The amount of damage done depends not only on the kind and the amount, but also on the particular tissues exposed and the rate at which the dose builds up. Information is more accurate when dealing with single large doses than it is for the effects of chronic smaller doses of radiation. And lastly, we're going to look at some uses of radioactive isotopes in science and medicine. There are several radioactive isotopes that can be used in medicine. We tend to think about nuclear chemistry in terms of power plants and bombs, but actually radioactive elements are now used in many areas of science and medicine, and they are of ever-increasing importance to our lives. Because describing all of their uses would take lots and lots of books, we have selected just a few examples to illustrate the diversity of applications of radioactivity. Looking at nuclear medicine, the diagnostic procedures using nuclear chemistry are essential in medical imaging. 3 principal components to construct a radioisotope-based image. A radioactive isotope is administered as the element or incorporated into a compound that concentrates the radioactive isotope to be imaged, a method of detecting the type of radiation involved, and a computer to assemble the information from the detector to a meaningful image. The choice of a radioisotope and the manner in which it is administered are determined by the tissue in question. A compound containing the isotope must be absorbed more by the target tissue than by the rest of the body. All of the isotopes are gamma emitters because gamma radiation is preferred for imaging. It's less damaging to the body in small doses than either alpha or beta radiation. Here are different radioisotopes used for different parts of the body. Technetium-99m is used for more than 85% of the diagnostic scans done in hospitals each year. Here we can see that it's been used for imaging of a heart. It also will concentrate in areas of high activity like the thyroid. In a PET scan, a positron emission tomography, an isotope that decays by positron emission is incorporated into a carrier compound and then given to the patient. And here we can see a PET scan of the brain. To treat most cancers, it's necessary to use radiation that can penetrate the body to the location of the tumor. Gamma radiation from a cobalt-60 source is commonly used. Unfortunately, the penetrating ability of gamma rays makes it virtually impossible to destroy diseased tissue without also damaging healthy tissue. But this technique is a regularly sanctioned procedure and its successes are well known. Food irradiation. Refrigeration, canning, and chemical additives provide significant protection in terms of food preservation, but in some parts of the world, these procedures are unavailable, and stored food spoilage may claim as much as 50% of the food crop. Food can be irradiated with gamma rays from cobalt-60 or cesium-137 to prolong shelf life. Irradiation slows down or retards the growth of bacteria, molds, and yeast. For example, irradiated milk has a minimum shelf life of 3 months without refrigeration. The USDA has approved irradiation of meats and eggs. Chicken, for example, normally has a 3-day refrigerated shelf life, but after irradiation, it may have a 3-week refrigerated shelf life. An argument favoring this technique is that radiation is less harmful than other methodologies for food preservation. It offers greater safety to food workers because it lessens chances to exposure to harmful chemicals, and it protects the environment by avoiding contamination of water supplies with toxic chemicals. And that wraps up our section.